So we still have about 3 more problems, and then we're going to move on to the next topic, which is variation of parameters. Again, to remind you again, this method of term coefficients is restricted to equations. Remember, 2 conditions. On the left-hand side, all the coefficients have to be constants, right? And the right-hand side has to have what's known as a finite family. Everybody knows what a family is at this point. Okay. So this will be example 6, I believe, if I track. Okay, second order equation, y double prime minus 2 dy dx minus 2y prime plus y equals e dx. And again, I'm not going to do all the algebra, it just bores you, but you should do it yourself, okay? Because on the exam, I'm not going to do it for you, okay? So you got y double prime minus 2y prime plus y equals e to the x, okay? We look at this, we see, oh yeah, great. The coefficients on the left are constants, right? 1, negative 2, and 1. The right-hand side, e dx, that's a simple family, it's just e dx, right? But again, remember, what's the first step? Find the homogeneous solution. Okay, solve homogeneous equation. I write this over and over again because I want you to get into that habit. The first thing you do is solve the homogeneous equation. Okay, well, that's the old e to the rx business, right? So I get r squared minus 2r plus 1 is equal to 0, which is the same as r minus 1 quantity squared is equal to 0, right? So I get a double root, right? R1 equals R2. Remember, it's a quadratic, it has to have 2 roots, and we have to write both of them even though they're double. It's a double root. Okay. And what's the solution of the homogeneous equation, y sub c of x? Well, we got r equals 1, so it's going to be e to the x. And remember what we do for the double root. We just, to get an independent solution, we multiply that by x. C2 x e dx. Remember, it's a second order linear differential equation, so it has to have 2 linearly independent solutions. Don't write c1 e dx plus c2 e dx, right? It's only one function then. Okay. So, now we go to the non-homogeneous equation, and we see now, what's the family of e to the x? It's just e to the x, okay? But remember, we have to check, is that a homogeneous solution? Unfortunately, e dx is a homogeneous solution. So what's the rule? You multiply that by x, then you get x e dx. That's also a homogeneous solution. So therefore, the particular solution, y sub p of x, has to be some constant x squared e to the x. Right? That's the lowest power of x multiplying e to the x, such that it's not a solution to the homogeneous equation. If you had to put over here y sub p equals some constant e dx, or some constant x e dx, then you know what's going to happen? When you do L on yp, you're going to get 0. And then you're going to have the unfortunate situation of 0 equals e dx, which is not good, right? So even if you slip at this point, I just want to kind of give you a heads up and what to anticipate, okay? I can understand that, you know, you forget to check maybe, or maybe you just look at e dx and you say, okay, I'll make the particular x e dx, because you forgot to remember that that's also homogeneous. If you put it into the equation and you get 0 on the left and nothing on the right, a contradiction, you know that you made a mistake probably in the form of the particular solution. Okay, everybody clear on this? It has to be x squared e dx, because both e dx and x e dx are solutions to the homogeneous equation. Okay. So now we have that expression for yp, okay, and then you just calculate yp prime, okay, using the product rule. I'll get ax squared e to the x by differentiating that. If I differentiate the first guy, I get 2ax e to the x, or yp prime, I guess I can pull out, just make sure I did that right, ax squared e to the x plus 2ax e dx. I can pull out an ax e dx on this guy, right? That leaves me with an x, ax squared e to the x plus 2. Okay? And then I differentiate one more time, yp double prime, use the product rule, I get ax e dx, the derivative of x plus 2 is just 1, plus a parentheses x plus 2, now I have to differentiate x e dx. And in the product rule, I get x e dx plus e dx. And of course, you want to simplify that. I'm going to go through all the algebra, okay? So, the question is now, what's L on yp? If you put this all together, you'll find out that L operating on yp is equal to 2a e to the x. Okay? And putting that equal to e to the x, so we know that a is equal to a half, right? So the general solution, y of x, we know is the superposition of the homogeneous solution, which is right over there, c1 e to the x plus c2 x e to the x, right? And then the particular, which is ax squared e to the x equals a half, so it's a half x squared e to the x. Okay? Okay, most of the, this is just algebra, right? You came to yp double prime, simplifying it. And then, of course, what should happen is that you group things with e to the x. In this case, actually, all the other stuff drops out. It just comes out to be 2a e to the x, right? Because there's only one free parameter, a. Right? Okay. Any questions on that? Okay. Same procedure in all these. Okay. Now the next one is an initial value problem. Okay. Second order equation again, y double prime, second derivative of y with respect to x, plus y equals, okay, y double prime plus y is equal to, on the right hand side, let's do 4x plus 10 sine x. And then I want you to actually get the solution now. Y of pi is given as 0, and the derivative at pi, so its initial value problem, is given to be 2. So the problem is solve that non-homogeneous equation subject to two initial conditions. Y pi equals 0, y prime of pi is equal to 2. Okay? So first thing again, homogeneous solution. Okay, I got y double prime plus y equals 0. The auxiliary equation is simply r squared plus 1 equals 0. So r equals plus or minus r. And you have to remember the different solutions, right? When it's a complex number, alpha plus minus I beta, and then we got e to the alpha x sine and cosine. So in this case, you just get y of x, sorry, y sub c of x. Let me just see how the order I wrote it in. c1 cosine x, right, plus c2 sine x. Okay? You do have to have those things kind of like in your permanent memory, right? When the roots are distinct, when they're repeated, and when they're complex. Okay? So c1 sine, c1 cosine, c2 sine. Okay, now let's get the family of the right-hand side. Let's do it in pieces. What's the family of 4x? That's just going to be x and 1, right? Because 4x and its derivative, all its derivatives, which is 4, are linear combinations of x and 1. Now we need the family of the next term. What's the family of 10 sine x? It's going to be sine of x, cosine of x. And now why it's so important now to go back and see if any members of your family are solutions of the homogeneous equation. Well, you don't have to worry about x and 1, right? The homogeneous solutions are cos x and sine x, so those things don't have to be modified. But in this case, sine x and cos x are both solutions of the homogeneous equation, so we have to modify them. Again, if you forgot to do that, and you put for y particular, say a sine x plus b cos x, what would happen on LYP? You just go to 0, because they're homogeneous solutions. And you knew then, oh, I must have forgotten something, that they were homogeneous solutions. So what we'll do is we'll write something like this. I'll put an arrow here to say going that, okay, because they're both homogeneous solutions, I have to multiply them by x. So the family would be x sine x. That's supposed to be a brace for a set. And x cosine x. That's the particular solutions, or the form of the particular solutions. Okay, let's go over here now. So let's not get lost in the algebra. Remember what the overall strategy is, okay? We solved the homogeneous equation, and we found that it's a linear combination of sine and cosine, but these things are arbitrary constants. Then we get my particular solution, right? and then apply the initial conditions to the sum of those two. Remember I said that's why it's very important to use different notation so you don't mistakenly, like a lot of students have done, they'll take yc of x and then they'll apply the initial condition to that. But that's not what the problem says, right? Y, which is the solution of the inhomogeneous, has to solve that. Okay. So let's get the particular solution. Particular solution, you see how I wrote it over here? I got y sub p of x is equal to ax plus b. Okay, now where did the ax plus b come from? Well, it's from the family x and 1, right? A constant times that plus a constant times that. And then we need the family x sine x and x cos x. So let's just write that as plus c x sine x. I do cosine x first. Doesn't make a difference, but yeah, I want to be consistent. Plus d x sine x. Okay, so we've got ax plus b plus cx cos x plus dx sine x. And remember, that's why I use a different notation. Usually when I use little c's, that's to signify arbitrary constants, but we're going to determine numerical values for a, b, c, and d by demanding that yp be a particular solution. Okay? Okay, I'll just write some intermediate results over here. What's yp prime? Like, isn't a minus, I'm going to use a particle, so it's minus cx sine of x plus c cosine x, right? Particle on this is plus cap d sine x plus dx cosine x. And again, what I suggest that you do is that you simplify before you differentiate again. So we'll have the constant a over there. And what do we get multiplied with x sine x? I've got sine x, a d sine x from over here, and a minus cx over here is my sine x terms. And now about the cos x terms. I've got a dx cosine x and a c cosine x. Okay.
Those are parentheses, not C, right?
Yeah, these are parentheses here. I'll write a little clearer if I can. Right? It's the coefficient of sine x, right? Oh, that's a C. Is that what I wanted to have? Let's see. What do we got? I got a d sine x, and then a minus cx sine x, okay? And the cosine x, I got parentheses dx plus c, c cos x, and then dx cos x, okay? Parentheses. Okay, and now you got to do yp double prime to clean it up, right? Yp double prime. Let's differentiate this guy. So I get parentheses d minus cx times a cosine of x from there. Then differentiating that, I get a minus c sine x. Nice big C sine x. Then I got minus dx plus c, because 3 over cosine is a negative sign. And then finally, plus capital D cosine x. And again, you would clean that up, get all the sine and cosine stuff together, okay? The important thing now is then, okay, you gotta simplify yp double prime as much as you can, and then do yp double prime plus yp. That's the left-hand side, and I'll just call that L operating on yp. I'll give you the simplified form for that. You'll end up with a linear function, ax plus b, minus 2c sine x, plus 2d cosine x. So we've got ax plus b minus 2c sine x plus 2d cos x, and we know the right-hand side is 4x plus 10 sine x. Oops, sorry about that. Okay. Okay, and now we just match coefficients. Okay, let's match the x coefficients. I guess I get a is equal to 4, right? Right? Let's match cosine x coefficients. You notice I've got a 2d cos x. There's no cos x on the right, so therefore cap d must be 0 to be consistent. easy. Okay. What about a constant? I don't have a constant on the right. I got 4x and 10 sine x. Here I got a constant of b, so b has to equal to 0. And I'm left just with c now, right? Match the sine x coefficients. On the right I have a 10. On the left I have minus 2c, so c is equal to negative 5. Okay? So the particular solution now, minus the p of x, we go back, ax plus b, that just leaves me with a 4x, cx cosine x, which is minus 5x cos x, and cap dx sine x is 0 because d is equal to 0. Okay? So there's the particular. Okay. Now let's put everything together. Okay? If the problem stopped over here, if it just said find a solution at this point, you know, without the initial data, you could say y of x equals yp plus y sub c. But now we have an initial value problem, right? And again, this is why I'm very emphatic about using different notation. Who do I apply the initial condition to? It's y, which is the complete solution of the equation. Okay? So you should write down now the general solution y of x is equal to the homogeneous solution, c1 cosine x plus c2 sine x. And then add the particular plus 4x minus 5x cosine x. Okay, now we apply the initial condition. It's all at pi. Okay, so what's y at pi, my solution at pi? Okay, I get c1 cosine pi, which is negative c1, sine pi is 0, plus 4 pi, right? Then minus 5 pi cos pi is just plus 5 pi. And of course, that's simply 9 pi minus c1. Okay, but I'm told that the value of y of pi has to be 0. So therefore, we can solve for c1, and we find that c1 is equal to 9 pi. Okay? Now we just have to get c2. Okay? C2 involves what? The derivative of y at pi. So I got to take my expression for y of x over here, differentiate, plug in pi, and hopefully be able to solve for c sub 2.